This is an FEA simulation of two spur gears that have been brought into mesh. You will notice that in this particular case, I have fully constrained the inner bore on the right gear, and I have allowed the left gear to rotate about the central axis of that gear. On the left side, I apply a tangential load to the tip of the gear tooth, and then I allow the gear teeth to mesh at the pitch point. I did this so we could compare the direct bending stress on the tooth loaded at the tooth tip to the stress that is occurring in the gear teeth that are meshed. You will notice that the stress on the gear tip, you have to ignore the location of the applied load because that tangential load is going to generate very high stresses. What we want to do is look down here at the fillet radius at the root of the gear, and you can see that the stress is rather large at that location. And if I do so, you'll see on the order of 11,000 psi at the root of the tooth. Now, if I were to look at the contacting teeth, you would find much lower stresses. You'll see as I go into the root radius there, I have on the order of half the stress that I had at the root of the exposed tooth loaded at the tip, and that is because I have a contact ratio that's greater than 1. We can use the FEA simulation and we can compare a hand calculation of the stress at the root of the tooth that is caused by the tangential load applied at the tip of the tooth. We can compare these stresses directly to the Lewis bending stress that we do in hand calculations. We can also animate this to give you a notion of how the gears rotate and deform under the application of the applied load. This shows the large bending stress in the tooth loaded at the tip, but also shows the contacting stresses and bending that are associated with the teeth that are in the meshed region. I've used an exaggerated deformation so it's much easier for you to see. We spent some time talking about the forces that act between meshing spur gear teeth, and now we're going to take those forces and we're going to calculate stresses in a gear tooth. We will assume a contact ratio of 1 so that all of the force is carried on a single gear tooth. Now we are also going to ignore the radial load for the time being and just consider the bending stress that is generated by the tangential force that is acting on the gear tooth. That tangential force is going to cause bending about a plane here at a depth L from the top land of the gear. This drawing is not exactly precise, but we go from the top land to the bottom land, and we know that that distance is going to be the addendum plus the ddendum. And we know that for standard gears, it would be something on the order of 1 over the diametral pitch in the English system plus 1.25 over the diametral pitch in the English system. And so we can calculate what these geometries are. The other particular dimension we're going to need is the width of the tooth T down here at the base. And we're going to do a little finagling because we want to take a perpendicular from the fillet radius because it is at the base of this tooth at depth L, where we have the fillet radius, that we are most interested in the bending stress. And so we're going to just confine ourselves to this tangential force, WT, and we are then going to calculate a bending stress as an my over I term. Now, the moment generated by that tangential force, WT, is just going to be equal to WT times the moment arm, L. Furthermore, the height above the neutral axis, if you look at this geometry, our neutral axis is going to run down the center of the tooth. And so if we call the bottom width of the tooth T, then we are at a height T over 2 above the neutral axis. And so when we do our bending stress calculations, in our my over I formula, we're going to let y equal to t over 2, and our I is just going to be related to this rectangular cross-section of the tooth. And so I have here a drawing of a tooth showing the face width capital F and the tangential force WT that's applied to the top edge of the tooth. And we are looking at the bending stresses at a depth L from the line of action of WT across the section of width T and depth F. And so our bending stress is going to use the moment of inertia of 112 FT cubed. Our bending stress then becomes 6WT times L divided by F lowercase t squared, where that T is the width of the tooth at the bottom land. Now we want to express all of these bending stress terms in terms of things such as the diametral pitch. And so we're going to go through a sort of mental gymnastics to get there. And so we're going to draw some lines from the top land of the tooth. We're coming down a depth L, and we're going to proceed a little bit further to a depth X by looking at the intersection of that line down the center of the tooth with the normal to the fillet radius at the bottom land. And we notice that this is going to generate angle theta between L and a line that goes from the center of the tooth and just goes tangent to the fillet radius. So the fillet radius is down here, the top land of the tooth is up here, and we have the involute profile that connects down to the base circle. And so this angle theta in here is equal to this angle theta, which is right in there. We know that this distance here is given as t over 2, and we come down a depth x. Well, we're just doing some finagling here. So the tangent of theta is going to be equal to, here, t over 2 divided by L, and it's also true that the tangent of theta is going to be equal to x divided by t over 2. So we have that. And so x is equal to t squared divided by 4L. And we are going to go up and replace this t squared in the bending equation with a value that we get from this equation right here. And so we're going to let t squared equal to 4LX. We plug it into that bending stress equation and we get this term right here. And now what we're going to do is we are going to note that this 4 over 6 becomes a 2/3 times x, and I get rid of the L, so I can cross the L out. I end up with this WT divided by the face width F divided by 2/3 x, and now I'm going to multiply by 1 in the form of the circular pitch divided by the circular pitch, and I will get this equation right here. I'm going to create a new term, which I will call y, which is going to be equal to, I'm going to group the 2x and the circular pitch in the numerator, and so I put the 3 up there in the numerator as well. And so I find that my y is equal to 2x over 3p. And since the circular pitch is in inches per tooth and x is going to be in inches, the y is going to be a dimensionless quantity as shown here. And so we replace 2x over 3p with y, and we get this equation. And now we are going to replace the circular pitch with the diametral pitch and pi. So we're going to use that the circular pitch is equal to pi over the diametral pitch. And we end up with this equation right here. So now what we are going to do is we're going to go back to our relationship between small y and pi. We're going to collect those two together and we're going to replace it with a capital Y. And so that capital Y is pi times 2x over 3 times the circular pitch. And then we replace the pi over p in here with the diametral pitch. And so we end up with the bending stress is equal to the tangential force acting on the tooth times the diametral pitch divided by the face width times this factor y, and y is called the Lewis form factor. And there are tables for Lewis form factors. That Lewis equation for the bending stress, it is something that we are going to use when we compare finite elements and Lewis bending stress calculations. It's a simple equation, 14.2 in the Shigley text. The Lewis form factor y, which we just derived, is 2x times the diametral pitch divided by 3, and we use those equations to calculate the bending stress. Table 14.2 includes values of a Lewis form factor as a function of tooth counts. So you see that you can use this table for many different tooth counts, including a rack for a rack and pinion system. Now, it's important to note that the Lewis bending stress ignores the stress concentration factor, and it ignores the compression brought about by the radial load. So you do not really expect good agreement between the Lewis bending stress and a finite element calculation. Because gearboxes are running at significantly high RPM, there are always going to be dynamic effects which amplify the magnitude of the loads that are being applied to the teeth on the gears. And so we need to know pitch line velocities to make corrections that can increase the magnitude of the load and thereby increase the magnitude of the stress associated with a running gearbox. These are some examples of dynamic effect correction factors, KV, for different profiles. Cast iron with a cast profile. If we measure V in feet per minute in the English system, we have this velocity correction factor. For cut or milled teeth, we have this velocity correction factor. For hobbed or shaped, this one, and for shaved or ground, we use this geometric correction factor. These are equations 14.4a and b and 14.5a and b in the Shigley textbook. If we were measuring our pitch line velocity in meters per second, then we would use equations 14.6a through d. Now, we always use a dynamic correction factor for running gears, and if we incorporate that dynamic correction factor into the Lewis bending stress equation, you see that it shows up right here, and the metric version of this shows up in equation 14.8. This is a good time for an example problem. This will be an example from the book where we're taking a look at a stock spur gear having a diametral pitch of 8 teeth per inch, a 1.5 inch face width, 16 teeth, and a pressure angle of 20 degrees with full depth teeth. The material is AISI 1020 steel in the as rolled condition, meaning it is cold work. We are going to use a design factor of 3, and we want to rate the horsepower output of the gear corresponding to a speed of 1200 RPMs. So this question here is, what is the horsepower, or if we were in the metric system, what would the kilowatt be for a particular gear? Taking one step back, using the relationship between load and horsepower, or load and kilowatts. And so if we're going to be doing this in the English system, because all of the dimensions are given in the English system, we're going to use the velocity corrected Lewis bending stress equation. So that means that we need to know the diametral pitch. Well, we already have that. It is 8. We need to know the face width, F. We know that's 1.5 inches. And we have to make some other calculations because we are going to need the tangential loads, and we have to calculate pitch line velocities to do the velocity correction. So we want to find the rated horsepower. So the first thing that we will do is we'll design to prevent yield. And that means we need the yield strength for the material, and the allowable stress would then be equal to that yield strength divided by the design factor, which in this case is 3. So we look up the ultimate tensile strength for the 1020 as rolled, and we find that it's 55 kpsi. The yield strength is 30 kpsi. So the allowable stress for a yield limited design would be the yield strength of 30 divided by the design factor of 3, and that is just 10 kpsi. So we want to use that allowable stress in the Lewis bending equation and then use that to extract the horsepower. The Lewis bending stress equation has that velocity factor, the tangential force, diametral pitch, face width, and the Lewis form factor. So we are going to have to use a table to look up the Lewis form factor, and we're going to have to use the equations we just showed to find the velocity correction factor. But we will relate the tangential load directly to the horsepower using the equation that we presented in a previous lecture. So in order to get that velocity correction factor, we need to know the speed at the pitch line using the relation pi dn over 12. We know that d is the number of teeth divided by the diametral pitch. We have 16 teeth. The pitch is 8, so we have a 2-inch diameter. It is running at 1200 RPM, which gives me a pitch line velocity of 628 feet per minute. I go to table 14.2 and I look up the Lewis form factor for this 16-tooth gear, and I get a value of 0.296. So now we are ready to use the calculation for the velocity correction factor, we're going to use equation 14b, where the velocity correction factor is 1200 plus v divided by 1200, and our v is measured in feet per minute. So using that equation, we get a velocity correction factor of 1.52. So we are magnifying the applied load. And so now what we're going to do is use our power tangential force relationship, this 33,000 H over V, where H is in horsepower, multiply out this 33,000 divided by 628. So we have that the tangential load is 52.5 times the horsepower. We set the design allowable of 10 kpsi equal to the velocity correction factor times the tangential load, which is 52.5 H. We multiply that by the diametral pitch, which is 8 teeth per inch, divide it by the face width of 1.5 and the Lewis form factor of 0.296. We solve for H, and we get a yield limited design of 6.95 horsepower. Well, instead of yield, what if we wanted to do a fatigue design? It's still true that the bending stress is given by kV tangential force times diametral pitch divided by face width times the Lewis form factor. And keep in mind that as we rotate this gear, that gear tooth is loaded. The load drops to zero. It happily runs around and relaxes with no load on it. It comes back, it is engaged, and the load increases again. So if you were to draw a tangential load as a function of time, it would go from zero to a max and back down again. There would be this interesting sinusoidal load, and that means that we would have a sinusoidal load for the Lewis bending stress as well. And the stress amplitude would be half the max value, while the mean stress would also be half the max value. So this is a situation where we cycle between 0 and sigma max. The sigma max is given by the Lewis bending stress equation. So the stress amplitude and the mean stress are half the maximum. So if we want an infinite life, we're going to have to estimate the horsepower rating using a fatigue calculation. So to do the fatigue calculation, we always begin our fatigue calculations by doing a fully corrected endurance strength as shown here. And we're also going to need to calculate a fatigue stress concentration factor. We know that our first estimate of the endurance strength is half the ultimate. And since we know that our ultimate for this material is 55 kpsi, then our first estimate SE prime is 27.5. We're going to throw that up into here. We have to calculate a surface correction factor, which is given by A times the ultimate raised to the B power. Since we're measuring our ultimate in kpsi and it is a machined gear, we're going to use a factor of 2.7. We're going to use the design factor of safety of 3, and we're going to design it for infinite life, which means, because we have a mean and a stress amplitude, that we're going to divide the stress amplitude by the fully corrected endurance strength, the mean stress by the ultimate, and we're going to set that equal to our 1 over our design factor of safety. We have to do a geometric size correction factor, KB, but we might as well just jump ahead to the loading factor. We're in bending, so we're just going to use a load factor of 1. This is from equation 626 in Shigley. For the geometric size correction factor, we need to find an equivalent diameter, and this tooth is rectangular in cross-section at best. And so we need to take that rectangular cross-section and convert it into an effective area from which we can extract an equivalent diameter for a circular cross-section bar. That is what this is all about here. And so the equation that we have for that is that the equivalent diameter is 0.808 times the square root of h times b. So we need to know h and b. And we can just do that from our face width and our tooth width. So our first estimate of the endurance strength we already said. Our surface correction factor turns out to be 0.934. For the size correction factor, we need h and b. And so we need t, and we also need F, well, F is the face width. That's easy to figure out. And L, you may recall, is equal to the addendum plus the dedendum, which is standard for gears. And so we know what those things are. So L is 0.28. This value X that shows up in the Lewis form factor is equal to 3 times the form factor divided by twice the diametral pitch. So it is 0.056. And from that X value, you may recall that the T squared is 4Lx. And so we find that T is 1/4 inch. Now that we have that, we can find the equivalent diameter of an equivalent circular shaft exposed to bending, and that DE is 0.49. We then use it in the geometric size correction factor calculation and find a KB value of 0.949. We're going to ignore the other correction factors. We're going to take our first estimate, SE prime of the endurance limit. We're going to multiply it by KA and KB, and we get a corrected endurance strength of 24.4 kpsi. We have already said that the stress amplitude is equal to the mean stress, which will be half the bending stress that we calculate from the Lewis bending stress equation corrected for velocity. But we also now need to figure out our fatigue stress concentration factor. For that, we need our fillet radius, and then we can use table A15.6 to find an elastic stress concentration factor. For our given gear, it's equal to 1.7. Our fatigue stress concentration factor is related to that through notch sensitivity. We calculate Q to be 0.62, and we find a fatigue stress concentration factor of 1.43. So now we know that our sigma A equals sigma M is going to be KF times 1/2 the maximum Lewis bending stress. We take 1.43 divided by 2. We throw our Lewis bending stress in there from this equation right here. We put those sigma A's and sigma M's into the Goodman mean stress correction factor. We substitute for WT using the horsepower equation, and we solve for that horsepower rating and get a value of 5.38 horsepower. So design to prevent fatigue failure requires a slightly smaller horsepower than the design to prevent yield.